Chapter 16, Data Representation. What are the learning objectives? They will show understanding of why user-defined types are necessary. User-defined data types. What are the data types you know? You know string, integer, boolean, real. Those are the built-in ones, normal standard. But here, you will understand why do you need user-defined? Because the user-defined types is you and I can define data types according to our needs. The built-in ones are done according to the programmer, the ones who supplied the language, Python language who created, according to their, not only their requirements, according to the requirements of the whole world. Those who are doing all over the world programming, their needs to suit everyone. But user-defined means when you and I define something which is specific to one of our programs, it will not suit any other user or most other users. So because of that, it can't be included in the library, system library, the language library. So those we have to do in our own programming. Then we'll know how to define and use non-composite data types. So that is one type of data type, non-composite, single ones. And you will also composite data types. There are non-composite data types and composite data types. Composites, non-composite single, composite is combined. Choose and design an appropriate user-defined data type for a given problem. But depending on the problems you are going to solve, there are very specific ones, 100% suitable for that application. So how to choose it and design. And you will understand the methods of file organization and select an appropriate method of file organization and file access for a given problem. You need files on the hard disk to save data. Whatever the data that is processed and output the information, you need a place to store them for later use. So that is files, and there are file types. Show understanding of methods of file access. So how you save and then how you access. Understand hashing algorithms. That is for checking the direct access method where the record is saved. Record is the component of the table. Describe the format of binary floating point real numbers. Binary floating point real numbers. The decimal point is floating. And understand the effects of changing the allocation of bits to mantissa and exponent in a floating point representation. Mantissa and exponent, the two parts of the number. Convert binary floating point real numbers into denary and vice versa. Normalizing floating point numbers. Understand the consequences of a binary representation only being an approximation to the real number it represents in certain cases. When you approximate, because sometimes you can't give the exact one, then what are the consequences? Sometimes there are errors also. Show understanding that binary representations can give rise to rounding errors. So we are used to the denary system, and in binary, you round up also there are errors. We will know how they are detected and corrected also. Built-in data types. First of all, the built-in data types, we know the programming language defines a range of possible values that can be assigned to a variable when its type has been chosen. So if you say a equals 10, a is the variable name and it will be assigned a value of 10. What is this type? Is it a number 10, some road? Is it an address? If that is the case, it's not a number. But if it is a number of pens or something like that, then it's a number. So either integer or real or something. The data type, that's called the data type. What is the type of the data? Either it's string, integer, real, boolean. And also programming language defines the operations that are available for manipulating values assigned to the variable. There are certain operations which are applicable to each type. Now, if you enter number 10 or all the numbers of the houses on a street from the address given, you extract the numbers and then try to add, it won't give the total. It will give a string of the numbers because this is part of a string that you have extracted. So likewise, there are various limitations or what is applicable for that, what you can do and what you can't do about those types. Then what about the user-defined data types? Earlier, built-in data types are not user-defined, they are the language providers. User-defined data types is who is the user here. Normally, the user is the one who uses a program, application or stock control or anything. He doesn't know anything about the program that is done. Who is the user here? Programmer becomes a user of a programming language. Programmer includes the definition of a user-defined data type in the program. So the program only can include the definition of a user-defined data type in the program. Since the data type has been defined, variables can be created with the user-defined data type. So once you define, you can declare variables of that type. Then there's one confusion though about the stacks, queues, and linked lists. They are ADT. Do not confuse with the ADT about these things, user-defined. They are stacks, queues, and linked lists. Different types, right? Non-composite data type. First, we'll take the non-composite data type. No reference to another data type. The simple built-in data types such as integer or real are examples of built-in non-composite data type. So built-in because it's already available, and non-composite is the single type, single. No complications, no combinations. It is also possible for a user-defined data type to be non-composite. So if it is integer, only integer. If it's real, it's real. Nothing more mixed up. But user-defined types also you can do like that. Then comes enumerated data type. User-defined non-composite data type. User-defined, non-composite, like the integer real. When a specific enumerated data type is defined, every single possible value for it is identified. That is, all the possible values are identified, unlike in the built-in ones, where integer, you can enter up to a range, given range. Character, though one character, you can go up to, in capitals A to Z and in simples A to Z. There is no limitation of those things. But here, this is limited or given, predefined. Other than that, you can't enter something else. Just like you can't enter a name or age which is integer. Same way here, not only the type, but the data itself. But when you say age or name, there is no specified name given, no, or names. You can enter only Tom, Dick, or Harry, or something. No. But here it is given like this. T directions equals north, east, south, west. If you declare like this, just one, this is one definition. And there are only these will be accepted. It will not accept central or north central or something. Nothing will be accepted, be rejected. That is the thing. Every single possible value for it is identified. Pseudocode for two examples of enumerated data types, definitions. Type. This is a keyword to define in pseudocode. Type. T directions equals north, east, south, west. Now, if you say string, you can enter anything, no? Either north, east, south, west, or northwest, north central, or Mohammed, Tom, Somapala, all those things. Anything can be entered. String, not defined. But here it's defined. This is the data that is allowed. Only 4 data items. And here's another one, T days. T days equals within brackets Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. That's a weekdays. Then thereafter, variables can be declared and assigned values. So now we take these two as string and integer, which are already available in this system. Now we can use like this, declare direction 1. That's a variable we are going to use. And the data type, the usual way you put the colon and T direction. What is T direction? Coming from here. This T direction, the definition will be assumed by this. Then same way, start date. Yeah, going to use a variable called start date. And the type is T days, and it's this type. Afterwards, you can initialize or assign. Direction 1, that is the one that we declared here. Direction 1 equals north. So that we get the value north. Start day equals Wednesday. That is start day is this one. The values of the enumerated type look like string values, isn't it? Yeah, Monday, Tuesday, Wednesday, they look like string values, but they are not. The values must not be enclosed in quotes. So there should not be any inverted commas or quote marks. The values defined in an enumerated data type are ordinal. That means there is an order. This means that enumerated data types have an implied order of values. That is 1, 2, 3, 4, 5, 6, 7, like in an array, the element numbers. Here also there's an order. That is why it's called ordinal. So you can compare Monday to Tuesday. Tuesday is more than Monday. Tuesday is less than Wednesday. Something like that. A comparison statement can be used within the values of the variables of an enumerated data type. Comparison statement can be used with the values of the variables of an enumerated data. That means declare weekend. So here's another variable, the usual way we do. What is the type? Boolean. Then declare day. What is the type? T days. So this weekend gets a built-in data type Boolean. Day gets a user-defined data type, that is T days. Boolean is available for anyone in the world, whereas T days is available only to this programmer. If you are the one who is defining, only for you. Weekend equals, now here is a conditional statement. Weekend equals true if day greater than Friday. So day greater than Friday means it can be Saturday or Sunday. Look at this. You will know it's greater than Sunday. Greater than Friday, Saturday, or Sunday. Which means it's a weekend. Then, like that, you can use in your program. For example, you can ask the user to enter, user in the sense the user of the program, what you have made. Enter the day. So if he enters Saturday or Sunday, when you apply this statement, it will give out the output weekend. If you enter Wednesday or any other day, then it is not greater than Friday, so it will say not weekend, it's a weekday or something. Now look at the key terms, user-defined data type. Where the program includes the definition in the program, so that where the programmer includes the definition in the program. So in the program, the definition has to be there because it's not in the system library. Because not in the program library, you have to include it in the program itself. Otherwise, the program will not know what it is. Non-composite data type, a data type defined without reference to another data type, a single one. Enumerated data type, a non-composite user-defined data type for which the definition identifies all possible values. Enumerated, like a list of data. The enumerated data type is one reason why user-defined data types are sometimes needed, because it's so convenient. Imagine using a string for the week, the t-day, for the t-day variable. If you use string, very difficult. How do you compare weekend, Friday to Saturday and Sunday? Very difficult. So because of that, you have this data type. It's very easy then. There could not be a built-in generic definition of an enumerated data type because the possible values would not be known. So if you are doing about the weekday or weekend or the weekdays, then this you have to define. If you are doing something regarding chemistry or physics or some other application or some economic like price index or something, prices, then you can't have this enumerated data type with the defined data like north, east, west, south. You can't have the data known, no? Economic or chemical or physical. Other things you can't. Because of that, it's not possible to have enumerated data type for the whole world or the generic one to suit everyone. The values can only be known when the programmer has identified them in the type definition. So when you do the program only, you will need this. So at that time, you make it. Composite user-defined data type. Now we are coming to composite. As a definition with reference to at least one other type. So two or more. The record data type, that was there in chapter 13, the record data type. Although there could be built-in record data types, the expectation is for a record data type to be user-defined. So there is a record data type in the built-in library, but we want to know how we can define our own record type. This allows the programmer to create record data types with components that precisely match the data requirements of the particular program. Python does not support the use of a record data type. So we are doing pseudocode now. The class can be used in place of that, even in Python. A class is a data type which is used for an object in object-oriented programming. For a given object-oriented programming language, there are likely to be a number of built-in classes. Class, like a mold for an object. However, if a programmer intends to utilize the benefits of the object-oriented approach, then the programmer will have to create a number of user-defined classes. Okay, so that's understood. Then we come to pointer data type. So about classes we'll be learning later in a later chapter, more detail. Pointer data type. The value is a reference to a memory location. Just pointing at a place that doesn't have the value, but it points to the place where the value is. An example of the definition of a pointer type, which requires only the identification of a data type for which the pointer is to be used. This is the way to define type T integer pointer. We are using the T to make it easy to remember or understand that it's a type. T integer pointer equals this caret. The caret symbol is the integer. An example of the declaration of a variable of the pointer data type which does not require the use of the caret symbol. Declare my integer point, T integer point. So T integer point is already defined and or not assigned, and the number or the reference, the value is there. An example of the declaration of two ordinary variables of type integer and the assignment of a value for one of them. Declare number 1, number 2 as integer. Nothing new, normal way we do that. And assign 100 to one of them. Number 1 equals 100. That's the way. An example of an assignment to a pointer variable of a value which is the address of a different variable. My integer pointer equals at, this is the reference, at number 1. What is in number 1? An example of an assignment which uses the dereferenced value which has been stored at the address defined by the pointer variable. This assigns the value 200 to number 2. Number 2 equals my integer pointer, correct, into, not into, the sign is a 2. So the pointer variable 1 for which the value is the address in memory of a different variable. Only the address. Doesn't give the value, but it points, okay, this has the value which is necessary for this. Then we have set data type. A set data type allows the program to create sets and to apply the mathematical operations defined in set theory. You may have done set theory in mathematics. A set is a mathematical concept with important properties. It contains a collection of data values. There is no organization of the data values within the set. Within the set, there is no organization. Duplicate values are not allowed. That is important. Duplicate values are not allowed. Operations that can be performed on a set include checking if a value exists in a set, adding a new data value, removing an existing data value, adding one set to another set. That is also possible. Add one set to another set and make a composite set, combined one. Then we come to file organization. Whatever the file type, the content is stored using a specific binary code that allows the file to be used as intended. We store the data using a specific binary code that allows the file to be used as intended. So later on, we'll be using that file in different ways. A file is either a text file or a binary file. A text file contains data stored according to a character code. That is, if you take the notepad and type something, that will be text document. That will say that, right? But not, again, you must realize that it's not A, B, C, D, but it's 001, something like that. But the type is different. You say this goes as a text file. With it, yeah. So there's a particular character code for that. if you have, for example, 1, 0, 0, 0, 0, 1, that means in binary it's 65. Code for that is the character which is corresponding to that code is capital A. According to that, with a text editor, we can create a text file to be used as input to a program. You can type like what I did now. We can create one. We can create a text file to be used as input to a program, where another program can access this and process. A program may create a binary file. So at the same time, this is what we did manually using a text editor. But you can create a binary file with a program. Programmatically, you can create a binary file as output from that program. It will be output to a file like this with the intention of subsequently using it for input. So same, just like we created this for input to another program, another program can create binary file as the input for another program. An integer value might be stored in 2 bytes in 2's complement representation. Integer value without decimal, it can be stored in 2 bytes in 2's complement representation. So that's one way you can save that. For a text file, the number of data in items per line must be known. So you must know that number of items per line. These are the, you open the notes where you can earlier. Remember I said character, but any character. String, if there is a limit of 256, depends on the language. Integer, if it says minus 128 to plus 128, that's the same way here, how you declare all that's coming. So there are like files. Master file, transaction file. Okay, so let's see. For a text file, the number of data items per line must be known. Let's take an example from this, the notes file here. 1, 2, 3, 4, like that. For one line, how many data items? If you have something like this, text file, data 12, 12. Likewise, you can completely like this. How many per line? 1, 2, 3, 4. That must be known. That is what this means. For a text file, the number of data items per line must be known, and the number of characters per item must be known. That is not, they are different, no? The first item has only 4 characters. Here also 4. Here 1, 2, 3, 4, 5, 6, 7. So you have to have how many? Now here you can't have 4 because the next one has 1, 2, 3, 4, 5, 6. So it has to be 6. And then the blanks there. For those extra ones, the blanks. If not, separator characters must be used. So if it is not there, the number, then you have to have a separator character, like maybe a comma or maybe semicolon or a colon, semicolon. Then of course, no need of spaces and all that. Also, end of line. Say something like this, we can define it in advance, right? If not, separator characters must be used. end of a line has an end of line character. So for that also you must specify. So what you have something like this, just one line for the whole file, but we know that there are two lines because of this character here. So the next one will not be taken for the first line. It will be taken as separate one as also the number of characters not necessary because we have used the end of line, end of item, end of data item character. So because of that, the data item is known. This is the end of it. Otherwise, you have to give the space, the number. How many characters? The organization of a binary file is based on the concept of a record. Binary file, the number of fields per record must be known. If any of the fields represent a string, the length of the string must be known. So for the binary file, the concept like a record. For a binary file, the number of fields per record must be known. This is one like that. Number of fields. This is one field, this is another, this is another. Likewise, in a record, normally you know the database structure. Number of fields per record must be known. If any of the fields represent a string, the length of the string also must be known. So the customer name is here. If that has to be a string, then that also you must know the length or the size of the field. For any other field, the internal representation will define the number of bytes required to store the field value. So in that case, if it is an integer or something, then you must know size, how many bytes. There is no need for the field separator character for an end or an end of record character because record has separately defined the data items and all that. The fields, they are fields defined. So no need of end of data item character or end of line character. It's not a line really, it's a record. So the end of record is known. Binary file, a file designed for storing data to be used by a computer program. File designed for storing data and to be used by a computer program. Computer program will use this binary file as input. Record is a collection of fields containing data values. A collection of fields containing data values. So each field will have a data value. This is a type of file, serial file. Records are not organized. That is, there is no order in the records. A typical use would be for a bank to record transactions involving customer accounts. That is like, when a customer comes at 9 o'clock or something, he deposits 1,000. So this is recorded. Then another one comes, withdraws 500. Customer 8 comes, deposits 750. Again, customer 1 comes, 500. So there is no order here. 1, 3, 8, 1. Only order is the time order. It starts at 9 o'clock and then 9, 5, 9, 10. That's only. Each new record is simply appended. Appended means at the end. The only ordering in the file is the time order of data entry. So the time the data is entered, that is the only order. Otherwise, there is no. Then there's another type called sequential files. Records are ordered. So there is some kind of order there. That is why it's called sequential. Sequence is ordered in sequence. When you say in sequence, it's in order. The correct sequence, something like that. Then sequential file could be used as a master file for an individual customer account. So again, when we take this customer file. This is also another master file where all the customers are there. 1, 2, 3. But this has an order. The master file is in custom order. And if you want to update this, take the first one first, go to the customer A or the number 1 here, and 1000, add 1000 and update the balance. Then the next one is 3, so go to 3, customer C, and update. Then 8, update. Then 1 again, so go to customer 1 and update. Master file. Also, individual account also is possible, where the opening balance is there on the first of a month, then the debit, credit, and the balance. That is also possible. At regular periods of time, the transaction file would be read, and all affected customer account master files would be updated. That's what I showed earlier. Customer record is being updated here. As a key field for which the values are unique and sequential but not necessarily consecutive. Not be consecutive, but it has a order there. Need not be 1, 2, 3, 4, 5, 6, but it can be 1, 2, 3, 5, 8. Simply append the record that is in serial file with the intention of sorting the file later. So a serial file can be sorted later into a sequential file. Appropriate records copied to new file. Rather than inserting, records can be copied to a new file. That is, you know about this kind of storage, the tape, the spiral like tape from this spool to that spool, like songs and all that in a cassette tape. You get this. So what happens is, if you want to insert something, you copy from here to there. Take a blank one here, new one, copy, and when the place comes to add or delete or insert or anything, stop there. And if it is to add, you add it here in the correct place here. Then start again the recording or the transferring. You want to delete, you come to this place, stop this one. Then you go past this deleted one, then start again, so that the deleted one remains here. It won't be transferred to this. Insert, delete. Likewise, you can do various operations. Then it becomes a ordered one. Copy to a new file. In the same file, that's what you have to understand is, in the same file, you can't adjust records. You can't delete and go to another place and add or insert. It's not possible. So that's why you copy to a new file and new tape file and create. Then comes direct access files, mostly used. Sometimes referred to as random access files. Direct access can be achieved with a sequential file. Sequential file also. We think that when you say direct access, the hard disk. Yes, but sequential file also is possible. A separate index file is created which has 2 fields per record. The first field has a key field value, and the second field has a value for the position of this key field value in the main file. Here it is. 1. 1 is 1 here, customer 1. 3, the third one, the connection here is 2. So if you want to access 3, go to this place, take this number, and then go to that place. 8. 8 to go to this place and find is 3, then go to 3. 8 is sorry, that's a mistake. That's there. It is customer C. Yeah, this is customer C. It will go to customer C. I mean, it's just an example. So likewise, it has the record number here. Actually, it's like this. The third is a, this has to be second record from this. I'll take the other way around. It's easier because this both days is same. I have taken this as 8 and taken 3 as a. But we'll take this 2. It's 3. Record 3 in the master file. And this 8 is, no, the third record here is the 8th one there. So that way it's easier like that. It should be here. You can have it for this one, not that. So you can access this. How do you access between this? How do you access that? That's the index. A separate index file is created which has 2 fields per record. The first field has the key field value and the second field has a value for the position of this key field. 1, 2, 3. And this is the position. Where is this? 1 is in 1, 2. Yeah, the second one is 3. No? So for that, you have to go to 3. Then the third one is 8. Yeah, you have to go to this. Third one is 8. And you don't need to worry about that because this is only the pseudo code for that and how you work out, how you the direct access works. This hash is the more important thing. This is not really necessary. It's a normal index type. Alternative is a hashing algorithm. For this, the alternative is the hashing algorithm. One simple hashing algorithm is applicable. There is a numeric key field in each record. The hashing algorithm, one simple hashing algorithm is applicable if there is a numeric key field in each record. So in each record, right, the collection of fields, if there is one numeric key field, then it's easy. We are not using the algorithm here. We have done it in a separate place. But collision is the same address as is calculated for different field values. Where it should be, there are 2 fields, but the same location is calculated. This is the hashing algorithm is to calculate the location, the hard disk. If the same is calculated, then what happens? Use a sequential search. That is, sequential means one after the other later, afterwards, sequential for a vacant address following the calculated one. So you got the calculated one, supposing here. Then thereafter you look for a vacant one. The very first one is taken. Keep a number of overflow addresses at the end of the file. At the end of the file, you have to have this kind of extra addresses because if in case there's a collision, if the same address is given, then you can use one of those ones, extra ones. Have a linked list accessible from each address. Now we'll remember linked list, how you access the free list, which are available, the free nodes. So likewise, you can have it there. Then the file access. Serial file. Read the whole file record by record from the beginning until target record is found. So serial file is like, just go one by one. Start from the beginning, then go one by one. Read the whole file record by record from the beginning until target record is found. So if it is apple or something, start with grapes, pineapple, vegetable, all those things. Then you come to apple. Then only you stop. Until then, you go on. Sometimes a P might come before A, right? Pineapple. Because it's serial, not sequential. Serial, just one after the other, you go on checking. Then a sequential file is same way. But if the key field value is known for the record containing the wanted data, the process is faster because only key field values need to be read. Because at that time, you don't read the whole thing. First, serially, you read this one, custom A, 5001, all that is read. But if you know the, the key field, then you read only this. And when it comes to, if it is 5, you can direct, when you come to 5, right? Same method, serially you go. But you don't check everything. So it's fast. Yeah. Then direct access file. The value in the key field is submitted to the hashing algorithm. The same way that you created the location. Now when you submit that value, also it will give the location. This eliminates the need to read records from the beginning of the file. So directly you can go random and direct the same. Random access and direct access. More appropriate is the direct access. File access might also be needed to delete or edit data. When you want to add, edit, or delete data, you have to access the file. In sequential file, same as when a record was added, following deletion or editing, all remaining records are copied to the new file. I explained it earlier. Like this, you stop and then you continue to copy the rest. Direct access file, there is no need to create a new file because directly you can access that and change or delete or add. Deletion, set a flag. So when you delete in direct access file, you don't physically delete. You just put a flag to say that it's deleted, either asterisk or some kind of symbol, which tells the CPU or the program that it's deleted. Choice of file organization. Serial, direct, and sequential. Serial, the batch processing or data backups on magnetic tape. So why do choose, when you choose the method, what is the method? Serial for what? Batch processing or data backups on magnetic tape. So data backups, you can use this method and keep on just backing up, just copying. Or batch processing means this. Now you have this recorded or stored in the time order, not in any order. This is a serial file. Then after 1 hour, when the customers come, after 1 hour, this is taken and this master file is updated. That's a batch. Collect, the meaning is batch of transactions. That is a serial. And direct access is used if rapid access to an individual record in a large file is required. Take the example of ATM transaction. If you want ATM transaction, the balance should be checked. You can't use this serial type, no? But then you have to wait till this goes to the correct place and might take few minutes. Whereas direct access is just go to that place and then either give the cash or reject the request. That the direct access is essential. Sequential file, suitable for applications when multiple records are required from one search of the file. So in the sequential, one search of the file in one shot or one try. If you want multiple records, then this is the ideal. At this point, it is worth mentioning the difference between key fields in a file and primary keys in a database table. In the database table, the primary key values must all be unique. Remember, database, the primary key values must all be unique. This is not a requirement for key fields in any type of file. Just the key field is not necessary. Only the primary key only has to be unique. It may be sensible in certain applications to ensure key fields have unique values, but it is not mandatory. So anyway, it's suitable, advisable to have unique values for key fields. Now we come to another section, real numbers. Now 25.3, the number 25.3 might be written as 0.253 into 10 to the power 2. That is because this decimal point has been taken two places this side, to 10 to the power 2. Each place is 10 to the power 1. So this is the same, no? Like multiplying by 100, again this goes there, 25.3. And it's same as this, 2.53 into 10 to the power 1. Or 25.3 into 10 to the power 0. That is the same number, 25.3 multiplied by 1. Or 253, you have taken this to the right and taking it back by multiplying 10 to the power minus 1. If a number is very large or very small, the exponential notation is the only sensible choice. Very large or very small, you have to use the exponential notation, otherwise it's not very effective. Floating point and fixed point representations. So for that, we have to learn this. Binary code must be used for storing a real number in a computer system. Binary code must be used for storing a real number, that is with the decimal point, in a computer system. One possibility is to use a fixed point representation. One is fixed point, a defined number of bits for the whole number part and the remainder for the fractional part. Right? So many for this part, integer part, and so many digits for the fraction. The alternative is a floating point representation. The format for a floating point number can be generalized as plus m into r e. That means a defined number of bits are used for what is called the significand or mantissa. So this is the mantissa, m, plus or minus m. Remaining bits are used for the exponent or xrad, e, the remaining bits. That is, so many bits for the mantissa, so many bits for the exponent. The radix r is not stored in the representation. R has an implied value of 2. So no need to have that. No, it's known. It's 2. Known value of 2. So you have to remember that. Floating point representation, a representation of real numbers that stores a value for the mantissa and a value for the exponent. Not fixed. Let's consider that a real number is to be stored in 8 bits. Fixed point option. A possible choice would be to use the most significant bit as a sign bit and the next 5 bits for the whole number part. I hope by now you know what is most significant bit and least significant bit is. This side is the most significant, we have more value. This side is the least significant, less the least value. This would leave 2 bits for the fractional part. So how many? Sign bit, that is the first one is a sign. And the next 5 bits, 1, 2, 3, 4, 5 for the whole number part. And then you will notice that there's a space here. This would leave 2 bits for the fractional part. So we have left 2 for the fractional part. Description. Largest positive value which can be taken by this number of 1 byte. Altogether 2, 7 and 8. This one is the sine. So this is positive. And 1, 2, 3, 4, 5. 1, 2, 4, 8, 16. 16 plus 15 is 31. If you know the shortcut. Otherwise, you have to add up 16 plus 8, 24. Or like that, you have to add up. Then you get 31. Shortcut is 1, 2, 4, 8, 16. 16 plus 1 less than 16 is 15. 16 plus 15 is 31. So 31. Then this one, hope you remember. If not, how do you calculate the decimals in binary? Take this one. Our usual one is 1, 2, 4, 8, 16, 32. You go on. That is 2 to the power 0, 2 to the power 1, 2 to the power 2. Now this is the decimal point here. This side what happened? 2, 1, 0, minus 1, minus 2, minus 3, minus 4. That means 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, 2 to the power minus 4. You go down, no? Coming down, you count down. This way, 2 to the power 3, 2 to the power 2, 2 to the power 1, 0, then 2 to the power minus. No? After 0, you have to go down. So 2 to the power minus 1, as you know, it's 0.5. And 2 to the power minus 2 is 0.25. You can calculate mathematically and see. Or you can even, let's say, I will take this and put it in the equal 0.5. Make it minus 2, half of it, minus 2, 5. Natural, no? You are going 1, 2, 4, 8, 16. That's halving, no? 16. Half of that is 8. Half of that is 4. Half of that is 2. Half is 1. Then half of 1 is 0.5. Half of 0.5 is 0.25. Half of that is 0.125. Half 0.0625. So that's logical. So this is then how much? Point 0.50. Second position is half of that, no? 0.25. So the total is 0.75. So we got this integer part as 31, and after decimal point 0.75. Smallest positive value is the smallest one is 0 now here. So this is 0 means positive, and 0.25, 0.01. You can't have anything smaller than this. 0.01. This is the smallest. 0.01 is like this. This one 0.25. The second position. So that's the smallest positive number in binary, 0.25. The smallest magnitude negative value. So this is 1 for negative. You already know that. And the smallest one is here. So minus 0.25. 0.1 is 0.25. And the largest magnitude negative value is, this is 1, all ones. Largest is all ones. So the first one is negative. So we put the negative sign here. And as we know this as 31 and 75. These two, 0.5 and 0.25, 75. Example, fixed point representation using sign and magnitude. So this fixed point, 2 places. Floating point, how do we do floating point? Floating point option. Possible choice would be 4 bits for the mantissa and 4 bits for the exponent, with each using 2's complement representation. Remember that also, 2's complement. The exponent is stored as a signed integer, right? The exponent. The mantissa has to be stored as a fixed point real value. Mantissa has a fixed point real value and exponent as a signed integer. The question now is where the binary point should be, because it's not fixed. Take this example, coding a floating point real value in 8 bits, 4 for the mantissa and 4 for the exponent. So first bit pattern for a real value, 4 is the 4 for the mantissa, 4 for the exponent. So if you take this 0, 1, 1, decimal point 1, that is 1, 1 is 3 and 0 is positive, 3.5. Okay, 3.5, the real value in denary. In denary, the real value is that. Decimal 1 is 0.5 and this one positive 1, 1 is 3 and this is 0, 3.0. This is 2.5. Then minus 3, 0, because this is minus. The first bit is minus, then it has to for it to be 3, then 1, 2, 4. Now remember, this is what we have learned earlier. This is the minus value here, minus 4, and the total of here is 1. So minus 4 plus 1 is minus 3. Same way here, minus 4 plus 0.5, that is minus 3.5. And here it's minus 4. That's all. Okay. Then second bit pattern for a real value. 0.111. Real value, right? So how much is this? Because it's 0, it's positive, and only the denary. 111 is 875 because 0.5 plus 0.25 plus 0.125. That gives you 0.875. Here it's positive and 0.5 plus 0.25, 0.75. Likewise, you get those numbers there. And this is minus, and the calculation comes here. Integer bit pattern. Now you don't have to, I don't have to explain this, you know it, 7, 6, like that. This is minus because the 4. This is minus, sorry, 1, 2, 4, 8, sorry. 4 bits now, 8, 1, 2, 4, 8, plus minus 8 plus 2, that is minus 6. Minus 8 plus 1, minus 8. So precision and normalization. You have to decide the total number of bits to be used and decide on the split between those representing the mantissa and those representing the exponent. Okay, again, you have to decide the total number of bits to be used and decide on the split between those representing the mantissa and those representing the exponent. Left side one and the right side one. Mantissa and the exponent. Increasing the number of bits for the mantissa would give better precision for a value stored. So remember, I have highlighted this, you have to memorize this. But would leave fewer bits for the exponent, which reduces the range of positive values. So I have summarized this here. Number of bits for mantissa, if it is more, then better precision. So mantissa for precision. Then exponent becomes less when because if it is say 8 and mantissa is increased, the balance is the exponent, it gets reduced. Then reduce range of values. The range of values is less then. Number of bits of for mantissa is reduced, the opposite of that happen. Then low precision and exponent becomes more, then increase range of values. So precision is one thing, the range of values is another. How are you going to remember this? This is a very difficult thing to remember. Remember like this, mantissa and mansion. Can you remember mansion, a big house. So precision, mantissa connected to precision, because mansion you can remember. Then the exponent is reduced, connected to range. Think of X-ray, and mansion, X-ray and mansion. X-ray will give you range, exponent range. Mantissa will give you, mansion will give you mantissa and precision, mansion. Like that. So you have to use those methods to remember, otherwise you will mix up those values. Now look at this, denary representation, floating point binary representation. Alternative representation of denary 2 using 4 bits, each for mantissa and exponent. Using 2 bits, 4 bits, sorry, denary 2 using 4 bits. So if you write 0.125 into 2 to the power 4, what happens? What is the answer? 0.125 multiplied by 2 to the power 4. If you take it this way, we'll take the first one. 0.5 into 2 to the power 2. How much? Means 0.5 multiplied by 2 to the power 2 means 4 plus 2. 2, no? 0.5 into 4 is 2. What is this? 0.25 multiplied by 2 to the power 3 means 8. Is equal to again 2. Then the other one, 0.125 power 4 means 16. If you calculate, you will know. It is that. 2. Alternative representation of denary 2 using 4 bits each for mantissa and exponent. So look at this side, mantissa and exponent. This is the mantissa. Positive. Take this one first. Positive, this is a 4 and multiplied by 2, right? Mantissa and exponent. For floating point binary representation is that. Look at this now, 0.125. 0.125 into 2 to the power 4. This is the 2 to the power section. 1, 2, 4. The value is here 4. And this, then now this is the denary, the decimal point. So if you take the value of this 0.5, 0.25, 0.125. The place value here is 0.125 here into 16 means 2 to the power 4. 1, 2, 4. 1, 2, 4. The value here is 4 for the exponent. Exponent means, and that you said that we knew that the 2 is implied. We don't write the 2 there, which implied 2 to the power 4 is 16. And this one, this is, now this is a decimal point, this is positive decimal point, 0.5. Here the value is 0.25. 0.25 multiplied by 2 to the power 3. 2 to the power 3 is 8. Here, this is how we got it. And the last one is 0.5 is this. No? The very first decimal point is 0.5. And multiplied by 2 to the power 2. 2 to the power 2. This is 1, 2, second position. 2 to the power 2 is 4. So 0.5 into 4 is 2. So different ways of representing denary 2. The minus ones. Denary representation negative 0.25 into 2 to the power 4. Likewise, the earlier, no need to go there. You can try this here. Point 0.25. Right? So 0.25 2 to the power 4, which is 16. How much? 0.25 is quarter, no? Quarter of 16 is 4. Here, 0.5 2 to the power 3 is 8. Half. 0.5 is half, no? Half of 8 is 4. Then 1 and into 2 to the power 2 is 4. So same number, no? Binary 4. Use this and look at this one. Negative. All three are negative, so there is 1 here. Then 1, 1, 0. 1, 1, 0. And this is 1, 2, 4. So this is 0.25. Because how do you get 0.25 here? The value of this is minus 4. Right? Minus 4. If you take this 1, 1, 0, how does it come? This first one is minus value. After the denary, after the decimal point, the minus value, first one is minus 0.5. Minus 0.5. And this plus, the balance, rest of it is plus. No? So the second position is 2.5. Second position, half of that, no? 0.25. Positive. Equals minus 0.25. Minus 0.25. And multiply by how much? Two to the power how much? 4. 2 to the power 4 here. 1, 2, 4. 2 to the power 4 is 16. Then how much? Minus 0.25 into 16 is a quarter. Quarter of 16 minus 4. Next one is the value here is minus 0.5, sorry. Minus 0.5. the power 3. Power 3, which is 8. The answer is 8, 2 to the power. So half of 8 is 4. Nothing here. Sorry, 1 into this is 2 to the power 2. 2 to the power 2 is 4. So 1 into 2 to the power 4 is, sorry, 2 to the power 2. 0, 1, 2, that is 4. Equals then we go to conversions. Conversion of representation. Conversion of real numbers. 4.75 equals how? How come? This 4 is 1, 2, 4. These are just real numbers. Don't worry about the other things and whose complement, nothing coming there at the moment. 4.75. Simply convert 4.75 into a real number. We have not done this before, no, because we were doing only integers. Now the real numbers. So 4, this part is 1, 1, 2, 4, that is 1, 0, 0 is 4. Then from the decimal point onwards, how do you get 75? 0.5, 0.25 when you add up 0.75. Okay. So only thing is you add a 0 in front. Add a 0 in front. So it's a positive. 0, 1, 0, 0, 0.11 is positive 4.75. What happens to this? Minus 4.75. First thing is this, you take this one. There we already converted the number 4.75 without the sign. Without the sign, it's this. Then you get the ones complement, that is by inverting this number. This one inverted 1, 0, 1, 1, and these two decimal ones become 0, 0. Plus 1, this is the usual two's complement conversion. Plus 1 will be added here. 1, same thing. That's a two's complement. So let's check whether it's correct. This is minus 8. The value of this is minus 8. Then there's no value there, 0. Then 1 is 2 here. That one is 1 here. Plus, there's no value here. So 0.25, second point. 0.25 is when you add up 1, 2, is 3. 3.25 is the positive side. Minus 8, positive 3.75 is minus 475. So that's correct. The calculation is correct. Now here's a worked example, converting a denary value to a floating point representation. Let's consider the conversion of 8.75. This is important for the exam. The 8 converts to 1, 0, 0, 0. Adding the sign bit gives 0, that is 0 for positive, 0, 1, 0, 0, 0. The 0.75 can be recognized as being 0.11 in binary. Correct? No, 0.11, 0.5 plus, in denary 0.5 plus 0.25 gives you 75. The combination gives 0, 1, 0, 0, 0, 0.11, which has exponent value 0. Right? Which has exponent value 0. Shifting the binary point gives, that is, how many places? Which has exponent value denary 4. That is, you shift this 1, 2, 3, 4 up to the leaving only the 0. You take it 4 places, which has exponent value denary 4. The next stage, depends on the number of bits defined for the mantissa and the exponent. If 10 bits are allocated for the mantissa and 4 bits are allocated for the exponent, the final representation becomes 0, 1, this one. See, you take this 0 also, 0, 1, 3 zeros here, 3 zeros, 1, 1, and what is the 3 zeros? If they, what's the size of the 10 bits are allocated for the mantissa? So you make it 10 here. 1, 2, 3, 4, 5, 6, 7. 7 up to this one is 7. Then you add 3 more zeros. Very simple. Add 3 more zeros to make it 10 for the mantissa and 0, 1, 0, 0 for the exponent. How? Now there is no, these are all gone. These decimal points are all gone. This is a new thing. Because we found exponent is 4 because we shifted this decimal point 4 places. So exponent 4 means this, simply 4. So the answer is this, a space, and this. 10 bits are allocated for the mantissa and 4 bits allocated for the exponent. So 4 bits here and the value here is 4. Example 2. Let's consider the conversion of 8.63. The first step is the same, but now the 0.63 has to be converted by the multiply by 2 and record whole number parts method. This works as follows. So that's a new one. Have a good look. How do we do that? New method. 0.63. Because 8 is no problem. What is the 0.63 we have to convert? So 0.63. See the method. Multiply by 2 and record whole number parts. So multiply by 2. 1.26. So 1 is stored, this one, whole number, to give the fraction 0.1. Then you take the fraction here. The answer, the decimal part of that, take here and multiply by 2, which gives you 0.52. So there is no integer here. Whole number part, 0. 0 is stored to give the fraction 1.10. This 0.1 is there. To that you add 0 because there is no integer part here. If there was 1 here, would have got 1. And then 52 is the fraction here, decimal part. Multiply by 2 again. Then you get 1.04. Now you can take 1 and add 1 to this one. 101. Now the remainder here, the fraction part here is 04. So 0.04 into 2 equals 0.08. Again, there's no whole number, so 0 is added. So 1010. 0.1010 is the answer. At this stage, it can be seen that multiplying 0.08 by 2 successively is going to give a lot of zeros. See, if you want to get another 1, you have to go on multiplying by 2. It be 6, 1, 1, 6, 3, 2, like that it goes on. The binary fraction before another one is added. So the process can be stopped. So therefore, normally in denary also, if you divide 10 by 3, what happens? 3.3.33333 goes on. But so you stop after about 4 places, you stop. Same way here, we stop it here. 0.63. Now when you take it, how much? 0.63 has been approximated as 625. Why? This, if you take this part, will be, here it's 0.5. Plus, there is no value here. But here, 0.125. How much? 0.625. But we started with 0.63. 0.63, the value we get is 0.625. So following steps 3 to 5, following steps 3 to 5 here, these things. Example 1, the final representation becomes this, right? If you calculate that, the 8 is 1, 2, 4, 8, right? 8 point this 1, 0, 1, 0. And how many places you've taken? 4 again, 4 places. Again, 4 places, same as this. So easy, similar, no? 4 places. So then you make this 10. You add the 0 in front and count with 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. And add the two zeros to make it 10. Mantissa is 10. And for the exponent is 4 places, 1, 2, 4, because we shifted these 4 places here. So that is, there is an approximation. It's not exact. So there are rounding off errors also in this. Problems with using floating point numbers. Conversion of a real value in denary to a binary representation almost guarantees a degree of approximation. That is not real exact approximation, close. There is also a restriction of the number of bits used to store the mantissa. That is also another problem. There's a limitation. Floating point numbers are used in extended mathematical procedures involving repeated calculations. Example, in weather forecasting, economic forecasting. They are repeated ones. Then what happens? The errors get more, no? Magnified. Very slight errors, when you do repeatedly, can result in big errors. Rounding errors can become significant if calculations are repeated enough times. The only way of preventing the errors becoming a serious problem is to increase the precision of the floating point representation. So now it's a bit of revision. How do you remember the precision? Or else how to increase the precision? We have to increase the corresponding part of it. What is the corresponding part for precision? Remember the word mansion I told you? So it's mantissa. So if you increase the mantissa, then the precision is of the floating point representation. The other one is X-ray, range. If you want to increase the range, then you increase the exponent. If you want to raise the precision, you increase the mantissa. Some languages, double precision or quadruple precision. So some languages have the precision to a higher degree. Not all. So that is the end of this chapter.